So we'll start just a quick revision of what we have discussed yesterday, that electrical charges and electrical current. Current is rate of flow of the charges, like how many charges will flow through a wire every second. We call that as electric current. And related to electric current, we derived the transport equation I is equals to NAQV, where N is a number of the charge carriers in a unit volume, A is a cross-sectional area, Q is a charge, it's a fixed value for electron, and V is a speed at which the drift speed at which the particles will move through the wire. So first we'll start the continuation of the topic, as the Kirchhoff's first law is related to the current. So Kirchhoff first law. What is the statement of the Kirchhoff's first law? It's a simple law which relate the current in the electrical circuit. What it states that the total current or the sum of the current which enter at any point enter a point is always equals to the current So according to Kirchhoff's first law, that the sum of the current which enter a point is equals to sum of current leave the point in electrical circuit. Irrespective of the type of the circuit, we may have a series circuit, like two or more components are connected in series. We may have a parallel circuit and two or more components are connected in parallel, or we may have a combination of a series and a parallel, like some part of a circuit, some components are in series, others are in parallel. So we may have a combination of or a mixed circuit. So according to Kirchhoff's first law, if we take any point in the circuit, anywhere, like example, I took point A here. So what it said that the total current which entered this point will always be equals to the total current which leave the point. So example, from the battery 3 ampere enter. So how much current will pass through point A? 3 ampere. And how much current will leave the point? Also 3 ampere. Same way, if I take like example point B here, and there's a current of the 5 ampere. So how much current enter this point? 5 ampere. So how much current leave this point? It will also be 5 ampere. Same way, if we take like point C here, so how much current, say 5 ampere current is from the battery, that is divided, let's say like 1 ampere and 4 ampere. So the total current enter at that point is 5 ampere, and the total current leave the point is also 5 ampere. Same thing if we take point D, how much current will enter this point? So 1 ampere and 4 ampere enter, so total is 5. And how much current will leave the point? That is also 5. If I take point E here, so how much current will enter that point? 5 ampere, and how much current will leave the point? That's also 5 ampere. So according to the Kirchhoff first law, that the sum of the current which enter a point, any point in the circuit, is always equals to the current leave that point. So if we have like example, say this is and the point where we join the wires, we call that as a node. So example, if this is a node here, and we have 3 ampere, 5 ampere, 3 ampere, how much current will leave? So how we'll identify, like this is a node, so how much current enter? 3 ampere and 3 ampere enter the point. So the current leave the point should also be, total should be 6 ampere. So if this is 5 ampere, how much current will be this? This will be 1 ampere. So according to Kirchhoff's first law, node is a point where two or more wires combine with each other. We call that as a node in the electrical circuit. Where we combine like two mesh of the wire we call that as a node. So the total current which enter the point is always equals to total current leave the point. If we have another example, Say if it is 3 ampere and 1 ampere, what will be the value? Which current leave? How much current will leave? If 3 ampere and 1 ampere enter, how much current will leave? So the current which will leave, that is equals to 4 ampere. Same way, if we have the same question like this is 3 ampere and this is the current which is going out is 7.5 ampere. How much current will enter this point? So how much current will enter? So that will be 4.5 because this is 7.5. So total the current, the sum of the current which enter the circuit, enter at any point is equals to sum of the current leave the point. So if we have like 4 wires are there and we have say 3 ampere, 3 ampere, 5 ampere. So how much current is this? So what we do, we check the total current which enter. So how much current enter the circuit? The 3 ampere and 3 ampere. So the total current which enter the point, that is 6 ampere. So how much current should leave? The same amount of current should leave. If 5 ampere is here, how much is remaining? 1 ampere. So this will be 1 ampere. So in a electrical circuits, the total current enter is equals to total current leave at that point. Another example about the Kirchhoff's first law. So we have a point, a node is there, and the current of 3 ampere, a current of 2.5 ampere, and a current of 7 ampere. Now, what will be the direction of the current in this one, and what will be the value or the magnitude of the current? What will be the direction of the current for this one? Because according to Kirchhoff's first law, the sum of the current which enter is equals to sum of the current which will go out. So how much current is entering? The 3 ampere is entering and 2.5 is entering. So 3 plus 2.5. And the current which is going out is 7. But both sides we should have the same value. Both sides we should have the same. Like according to Kirchhoff's first law, which is also the conservation of the charge, that the total charge which enter at any point must be equals to total charge which leave the point. So if 3 ampere and 2.5 ampere enter a point and 7 ampere is leaving. So which side we are, so it means the current should enter here. And how much current should enter? Because the total current out is 7. So the total current in should also be 7, but this is 5.5. So how much is this value? How much is this value? So this will be, because the 7 is going out. So how much will enter? So it should be 1.5 should enter. So the entering will be 1.5 ampere. Is it clear, this idea about the Kirchhoff's law? So using the Kirchhoff first law, you can identify the direction in which the current will move. Either it can be in or it can be out. More examples about the Kirchhoff law. So we have 4 ampere, 3 ampere, 2 ampere. And you want to identify what direction the current will, whether it will be in or out. You have to work out the direction of the current. So when you apply the Kirchhoff first law, that the sum of the current which enter the circuit must be equals to sum of the current which goes out. So the current which enter a point, that is 2 ampere is entering a point and 4 ampere. So 4 and 2 are entering. How much current is going out? So 3 is going out. So the total current which enter must be equals to total current leave. So 6 ampere is entering and 3 is leaving. So what should be the direction here? Is it in or out? Because the total should be balanced. 6 is on the left. So there must be 6 on the right. So it means there must be 3 ampere which is going out. So 3 ampere of the current will goes out from this intersection of the wire. Is it clear, the Kirchhoff's first law? Any doubt in this? Yeah, I will repeat this example because according to Kirchhoff's first law, the total current which enter at any point must be equals to total current leave the point. So in this example, or I'll give another example, a similar example. So let's say you have these wires, a mesh is there, and say 4 ampere, 3 ampere, 5 ampere, 2 ampere, 7 ampere. Okay. You want to find what is the current in this one and the direction. So when you apply the Kirchhoff first law, according to Kirchhoff first law, the total current which enter at any point will always be equal to the total current which leave the point. So this current, like this is a point where all intersect. So this is a current which is going in. This is also a current which is going in. This is also a current which is going in. This is a current going out. This is also a current going out. So what is the current going in? 4 ampere, 5 ampere and 2 ampere is the current which is going into this point. And which current is leaving the point going out? That is 7 ampere and 3 ampere. So means what is the total sum here? When you add them, it will be 11. And what is the total sum here? It is 10. But according to Kirchhoff's first law, which is also a conservation of the charge, that the total current which enter at any point must be equals to current leave the point. So the current which enter a point is 11. The current which leave the point is 10. But it should not be 10. It should be equal. So means what is this current which we are finding? So means this should be 1 ampere. So 1 ampere and the direction will be out. Is it clear, this example? So this is known as the Kirchhoff's first law, that the total current which enter, if it, actually the current, if you say -1 means it's in opposite direction. So you don't, current is not a vector quantity, current is a scalar quantity. Even though current is having a direction, but it's a scalar quantity. Why we say current is a scalar quantity? Because it does not follow the vector addition rule. What is a vector addition rule? Like, let's take an example. If you have two forces which are acting on the object, so two forces are there which are acting on the object, like example 3 ampere and 4 ampere. If I change the angle between the forces, the resultant will change. But for an electrical current, say we have a wire which is carrying 3 ampere in one of the branch and 4 ampere in another branch. So if I change the angle, if I change this angle, the resultant current will not change. The total current, which is 7 ampere here, it will remain 7 irrespective of the angle between the two currents. So that's why, because the current does not follow the vector addition rule, or it cannot be added by the vector addition, that's why current is having a direction. We say a conventional current from positive to negative, but it is not a vector quantity, it is a scalar quantity. And what is the reason for that? The reason is because it does not follow the vector addition rule. Like because according to vector addition rule, if you change the angle between the two vectors, the resultant will change. But in case of a current, the resultant will not change. Irrespective, if I change this angle between the two wires, if it will not change the resultant current. It will remain same. Any doubt in the Kirchhoff's first law? Any question or a doubt? Okay. Then the second topic is about the potential difference and the EMF, electromotive force. So voltage Voltage is a common term which can be used for both electromotive force and the potential difference. Voltage is actually divided into two categories. Voltage is how much energy carried by the charge or transferred by the charge. And it is divided into two categories. One is known as EMF, electromotive force. Another one is known as the potential difference or PD. So what is the meaning of the term EMF? Say you have a cell and it is labeled on the cell that it is 1.5 V. Which form of energy the cell is having inside the cell? Which form of energy the cell is having? Chemical cell. So it is having a chemical energy. So the cell is actually having a chemical energy. So due to a chemical reaction, the cell produces energy and it pushes the charges out. So on the cell, if it is labeled 1.5 V, what does it mean? It means that when one charge will come out, like one column of a charge will move out, how much energy it carry? It carry 1.5 joules. So the energy which this charge carry because of the chemical reaction, what we call that as electromotive force or EMF. So the EMF, it is defined as it is work done on unit charge. So how much work is done on a unit charge to move around a closed circuit, or how much energy is provided to a charge to move around the circuit, what we call that as EMF or electromotive force. But when this charge enter, like before it passes through a component, it is having 1.5 joules. When this charge move out, like pass through the component, it loses all of its electrical energy and then transfer into other form. Like if it's a lamp, it will produce a light energy. If it was a heater, it will produce heat energy. Or if it's a motor, then it will produce a mechanical energy. So how much energy is transferred by the charge? So it was having 1.5 joules and it has transferred all of its energy. So the energy transfer by the charge, what we call that as a potential difference. So potential difference, it is work done or energy transfer by unit charge when it passed through the component. So when the charge passes through the component, it will transfer energy and we call potential difference or PD. So if we need the voltage, voltage is work divided by charge. So how much work is done by the charge? A one coulomb of a charge, we call that as a voltage. And a voltage can be EMF, electromotive force. If the charge get energy by a chemical reaction, we call EMF or electromotive force. If a charge transfer energy when it passes through the component, we call that as a potential difference or PD. So one is work done on the charge and one is work done by the charge. So that is the main difference. Like how much energy is given to the charge, that is called EMF. How much energy is transferred by the charge, what we call that as a potential difference or PD. Is it clear, the difference between the EMF and the potential difference? Any doubt in this? Any question or doubt? So related to this EMF and the potential difference, we have another law of a Kirchhoff, that is a Kirchhoff's second law. According to Kirchhoff's second law, in a closed loop, the total EMF is always equal to total PD, potential difference. And that is also the conservation of energy. The first law is a conservation of the charge, that the total charge enter at any point is equals to total charge leave the point. And the second law is also known as the conservation of energy, that the total energy which is given to a charge will be equals to total energy transferred by the charge. Say we have two lamps which are connected in series. So we have two lamps which are connected in series and it is connected to a supply and it is labeled 10V. So what is the EMF? The electromotive force. The EMF is a work done on a unit charge. So the EMF is equals to 10V. Means when this charge will enter, a one coulomb of a charge will enter, it will carry 10 joules of energy. When this charge passes through one of the component, because we have two components, so it will transfer some of its energy. Let's say it has now 3 joules. How much energy is being transferred by the charge? So it was carrying 10 joules of energy and now it is having 3 joules. So how much energy is transferred? It has transferred 7 joules. So what is the potential difference here, or a PD? The potential difference will be 7, because potential difference is how much energy the charge transfer when it passes through the component. Same way, it has 3 joules of energy and it has transferred all of its energy. So what will be the potential difference? The potential difference will be 3. So according to the Kirchhoff's second law, the total EMF in the loop, the total EMF will always be equal to total PD in a loop. So what is the total EMF? It was 10. What is the total potential difference? First it was 7 and another one it was 3. So the total EMF is equal to total potential difference in a loop. Like when we make one loop, we'll get the total EMF same as the total PD. Which lamp is having a greater resistance, capability to resist the flow of the charges? Is it lamp 1 or lamp 2? Which lamp is having a greater capability to resist? So lamp 1 is having a greater resistance because more energy is transferred or more energy is used by the charges. So higher the resistance in the circuit, more energy the charges need to overcome that. That's why lamp 1 is having a higher resistance than lamp 2. If we remove lamp, this numbers I took randomly. It can be any number. I'm just saying, like first, if it is transferred 7 joules, the remaining 3 joules will be transferred to the other. But what if I remove lamp 1 or a lamp 2 and I use the same circuit, the same supply? Now what will happen? Like example, if we have a EMF of the 10 volts, so when one charge is entering a circuit, it will have carry 10 joule. Before it enter, it will be 10 joule, and once it passes, it will transfer all of its energy. Now what will be the potential difference? The potential difference will be 10. And according to the Kirchhoff's second law, that the total EMF will always be equals to total potential difference. So the total EMF is 10 and the total potential difference is also 10. So it is irrespective of the number of the component in a loop. We may have 100 components in the loop, but the total potential difference will always be equals to total EMF in one loop. If we have two components which are connected in parallel, and we have the same supply, 10 volts. Now we have two loops. What are the two loops? This is one loop and this is a second loop. So if we take the first loop, so if we supply 10 volts, the EMF of a 10 volts, so what will happen? The charge, when it, like this charge which enter, it will carry 10 joule. When it passes through this first loop, it will have 10 joules and there is no other component the charge has to pass, so it will transfer all of its energy. So how much is the potential difference in the first loop? It will be 10. Same way, when the charge is passing through the second loop, it will another charge will enter from the supply, which carry 10 joules of energy. Before it enter, it has 10, and once it passes, it will have 0. And it transfer all of its energy. So what is the potential difference in the second loop? So the potential difference in the second loop will also be 10. So when we have parallel circuit, we take loops, the total energy in loop 1 like the total EMF which was 10 and the total potential difference is also 10. And the total EMF for the second loop is 10 and the total potential difference will also be 10. So according to the second law, that the total EMF will always be equal to total potential difference irrespective of the number of the component connected, but the total PD will always be total EMF, electromotive force. Is it clear, this idea? Anyone having a doubt or a question? Okay. Now we will apply this Kirchhoff law, application of the Kirchhoff second law. Kirchhoff first law is very basic, but second law is a bit depending on the circuit, how it looks like. So I will give some examples of the Kirchhoff's law. How to apply a Kirchhoff law? Let's take a circuit you have. So we have, say, a 6-volt supply is there. And it is connected to a 2-volt supply. And then we have a lamp. 2 lamps are there. So this is a positive, negative. This will be the positive, negative. We have two, as you can see here we have 2 supplies which are connected. What is the direction of the electron, the conventional current? The 2-volt supply try to push the charges in this way. And the 6-volt supply try to push the charges in this way. Which is having a greater voltage, higher value, 6. So means the total net current will be due to the 6-volt. So when we take the direction, we take the direction according to the higher value. So which is having a higher value. So 6-volt is having a higher value. So this is the direction which we will take. Okay. So, and when we apply the Kirchhoff's law, say the current which is passing is I. We don't know that current. The current in the loop is I. And the resistance of the 2 lamps, one is say 10 ohm, another one is say 30 ohms. So when we apply the Kirchhoff first law of a circuit where here we have only one loop. So according to the first law, the total EMF in a loop must be equal to total potential difference. First, what is the total EMF? The 2 batteries are connected in opposite direction. Try to push. So what will the total EMF? It will be 6 minus 4. If they were connected in the same manner, like example, if it was 6 volts and 2 volts like this, like they both try to push the charges in the same direction, say 2 volts and 6 volt, both try to push the charges in the same direction, I will add them. But because in this case, the 2 supplies are trying to resist the motion of the charges as they are pushing the charges in opposite direction. So in that case, the total EMF will get by subtraction. So it will be 6 minus 2 is equals to total. Is it clear? The total EMF? Anyone having a doubt how I worked out the total EMF? Okay. Now the total PD, potential difference or a voltage, we just recall this formula V is equals to IR. You have studied in IGCSE that the Ohm's law, the ratio between voltage and current is always constant at a certain temperature. So V equals IR. So what is the voltage here? What is the potential difference or a voltage? So I is the current and R is the resistance. Or V is equals to IR, or you can also say V is equals to RI. It's the same thing. So resistance is 10 and the current is I. So I can say this will be 10I. Plus, what is the resistance? What is the volt potential difference here? The resistance is 30 and the current is I. So this we call as 30I. So when we simplify, this will be equals to 4 and this is equals to 40I. This will go there in division. So 4 divided by 40 is I. When we simplify, it will be 1 over 10 or 0.1. So means the current in this circuit is equals to 0.1. ampere. So using the Kirchhoff's second law, when we apply the Kirchhoff's second law, the total EMF will be equal to total potential difference. And using this, we can work out the current in the circuit. Is it clear, this example? This is a very simple. Okay, I'll repeat. So according to Kirchhoff's law, the total EMF will always be equals to total potential difference. Okay. That is what we said according to Kirchhoff's law. So when we take a loop, that what is the EMF? If the two batteries are pushing the charges in the same direction to get the total EMF, we'll add them. But in a loop, if two batteries or two supplies or two or more supplies trying to push the charges in opposite direction, we'll subtract to get the total EMF. So in this case, it will be 6 minus 2 because the total EMF, so the total EMF will be 4. What about the total potential difference or a voltage? We have the formula voltage is resistance into current. V equals Ri or V is equals to IR. So what is the voltage here? So voltage here will be 10 multiplied by the current which we said that is I. So 10I plus because the potential difference, or if you want me to write first I can write like V1 and V2. So I can say this will be, say, let's say this is V1 and this one is V2. So we can say it will be equals to V1 plus V2. What is V1 here, the voltage here? That is a product of resistance and current. So resistance is 10 and the current is I. So we say 10I. Plus what is the voltage here? That is the resistance which is 30 and the current is I. So it will be 30I. So when we simplify, this is equals to 40I. So 4 is 40I. So 4 divided by 40 is equals to I. So 4 divided by 40, that's equals to 0.1 ampere. That is the current which will pass through this circuit when two supplies are connected in opposite directions. Is it clear, this example of the Kirchhoff's second law? And then we can calculate the potential difference if we need the potential difference. So we know the current now. So it will, what will the potential difference it will be? It will be 10 multiplied by 0.1. So 10 multiplied by 0.1 means this will be 1 volts. And what is the potential difference here? It will be 30 multiplied by 0.1. So it will be 3 volts. So you can clearly see that in this circuit, when we have two supplies which are connected in opposite directions, and there are two lamps, one is 6 volt supply, another is 2 volt supply. We said the current is I, that is our assumption. And this is a 10 ohm and this is 30 ohm. So the voltage here was 1 volt and voltage here is 3 volt. Because the total EMF is actually equals to 4 volts. Another example, this is a very simple loop, like we have only one loop here. We don't have multiple branches in the circuit. What if we have the same example, but now we change the direction of the supplies? This is 6 volt. This is also, this is 2 volts. This was 10 ohms. This is 30 ohm. And now both are pushing the current in the same direction. So this will be the direction in which the current will flow. So according to Kirchhoff's first law, and the current which is passing through each component is I. So according to Kirchhoff's first law, the total EMF will be equals to total potential difference. That is the Kirchhoff's first law. What is the total EMF? In this case, because the two supplies are pushing the charges in the same direction, so the total EMF will be 6 plus 2. What about total potential difference? So here resistance is 10 and the current is I, so we call 10I. And then resistance is 30 and the current is also I, so we call 30I. When we simplify, this will be equals to 840I. When we divide 8 divided by 40, so means it will be 1 over 5 or zero point 0.2, you can say. So I is equals to 0.2 ampere. So now the current in the circuit is equals to zero point 0.2 ampere. And using this zero point 0.2, we multiply by the resistance, we can work out what will be the potential difference here. Like the resistance is 10 and the current is 0.2. So this will be equals to 2 volts, and the current, this resistance is 30 and 0.2. So this will be equals to 6 volts, the potential difference here. And the total EMF must be equals to total potential difference. Is it clear, this example about a single loop, which is a very basic type of question? Usually you don't have a single loop question, you have multiple loop question. I will solve more examples for the multiple loop, but for a single loop, is it clear? Anyone having a doubt or a question till this point? So the difference between EMF, it's energy transfer, but it's a work done on the charge, and the potential difference is work done by the charge when it moves around the closed circuit.